Welcome to GER of Mathematics and Statistics lessons. In today's video, I shall be talking about the rational number system. So the rational number system under real numbers is what we shall be discussing. But before we continue, please subscribe to the channel if you haven't subscribed yet. Make sure you smash a like on this video. Make sure you share our videos, you watch our videos, and most importantly, if you haven't subscribed, subscribe to the channel. Okay, thank you very much. Now let's begin. Now, what are rational numbers is what the focus of this video is all about. We want to answer the question, what are rational numbers? Okay, so the first thing I'm going to say is that rational numbers, or the rational number system is denoted with the symbol this, a double stroke Q. So it is not just any Q, but it is a Q that has two strokes. Okay, so this particular Q conventionally represents or denotes rational number systems. Okay, now the next thing I want to tell you is a definition of the rational number system. Now that we know that Q, this type of Q, represents the rational number system, then how do we define the rational number system? Using set builder notation or set theoretic notation, rational numbers constitute the set of all x such that x is equal to a over b. X can be expressed as a over b, and b is not equal to 0, and a and b are integers. Okay, so what this means is that rational number system contains the set of all numbers that can be expressed as a ratio of two integers. Okay, so in this system, all numbers that can be expressed as a ratio of two integers are accommodated. Now, what I want to tell you here is that the rational number system is bigger than the integer number system, and the integer number system in turn is bigger than the natural number system. What that means is that once a number is a natural number, automatically it is a subset of the integer number system. Okay, so if a number is a natural number, automatically it is an integer, and if a number is an integer, automatically it is a rational number. Okay, so the system of natural numbers is a proper subset of the integer system, and the system of integers is a proper subset of the set of rational numbers, okay, or the rational number system. That is what I'm trying to say. Now, take note, in this system, if you have watched our videos on natural numbers, you will notice that in this system, for natural numbers, we had numbers that were positive whole numbers. But in this system, the integer number system, we had numbers that were positive whole numbers, negative whole numbers, and 0. Then, in this system now, every number that can be expressed as a ratio of two integers are accommodated. Now, in this system Z, the set of integers, there are certain numbers that cannot be accommodated, and those are the ratios of two integers. For instance, in this system, you cannot have 6 over 7. Why? Because 6 over 7 is a fraction in its simplest form, a proper fraction, and fractions are not members of the integer system and are also not members of this system. So in this system, you do not have this. In this system, you do not have this. But there is a system that accommodates results like this, results that are in their simplest form and in fractional form, such that the denominator is not 0. That system is called the integer number system. So whereas 6 over 7 cannot be accommodated in n, the set of all natural numbers, 6 over 7 cannot be accommodated in z, the set of all natural numbers, or set of all integers. However, 6 over 7 can be accommodated in this system. Okay, why? Because this system accommodates results that can be expressed as a ratio of two integers, such that the denominator is not equal to 0. Okay, now the next thing I want to say about the rational number system is this. for the rational number system, take note of one thing. This system, in this system, you can actually express what do you call it? These fractions in decimal forms. And when you express them in decimal forms, certain characteristics will be seen about the rational number system. So I'm going to call this a decimal representation of the rational numbers or the rational number system. So decimal representation of the rational number system or rational numbers of the rational numbers. Okay, now if a number is a rational number, it means in fractional form it can be expressed, and it can also be expressed in decimal form. Now, what is the decimal representation of a rational number? Let's consider a rational number x. Let's call x a rational number. If x is a rational number, then it is possible to express x as a0 point a1 a2 a3 up to an, or as so on and so forth. Okay, so it is possible to represent this fraction a over b in this form. Okay, so it is possible to express a rational number as a decimal, and to do that means to write this rational number in this form. Okay, now if you want to know the properties of a rational number, aside every other property that may abound for rational number, if you want to know very serious properties of a rational number, or to identify that a number in decimal form is truly a rational number, then you can know by two things. If a number is a rational number and it is expressed in decimal form, either of two possibilities may arise. That decimal may be finite, or the decimal may be recurring. So rational numbers in decimal forms usually produce what we call finite decimals or recurring decimals. So what is a finite decimal? You can have rational numbers. When you have rational numbers in decimal form, giving you numbers like this: a0 dot a1 a2 a3 up to a fixed number ak. Okay, so notice that after the decimal point you have a fixed number of digits. Then if a fixed number of digits exists after the decimal point, then this kind of rational number, when expressed in decimal, is called a finite decimal. Okay, again, x, the rational number, can be expressed as recurring digits. Okay, it can be expressed as recurring decimals, and that is also another feature that can make you know that the number you are dealing with is a rational number. If the number you are dealing with is a rational number and it is not a finite decimal, it can happen that you have something like this: a1 a2 a3 up to ak as a fixed block of digits, followed by a set of recurring digits, such that you have b1 b2 b3 up to bn, repeating itself again after n: b1 b2 b3 up to bn. Okay, and then it repeats itself, it keeps repeating itself. Okay, now if you have this kind of occurrence, that when if a rational number is expressed in decimal form, it gives you, after the decimal point, probably a set of a fixed block of digits, and after that fixed block of digits it starts giving you repeated digits, then that kind of number automatically in decimal form must have come from a rational number. So two ways to know that a number you are dealing with is clearly a rational number, especially when that number is in decimal, is to look at the kind of decimal you have. If the decimal has digits after the decimal point that are fixed, that kind of decimal is called a finite decimal, and it tells you whenever you have a finite decimal can only come from a rational number. Again, if you don't have a finite decimal but a recurring decimal case, then a recurring decimal case can only have come from a rational number. Why? A recurring decimal simply means that after the decimal point, you may or may not have a fixed block of digits, but after a fixed block of digits, whether you have it or not, you will start having another block of digits repeating itself time and time again. Okay? Now, what I want you to know is that in the decimal representation of a rational number, A1, A2, A3, AK, all the numbers that come after the decimal point are digits. All the numbers, so this A1 here is called a digit, A2 is called a digit, A3 is called a digit. All the numbers that appear after the decimal point are called digits. Now, take note of this. Aside the fact that they are called digits, you must also know that the digits that can be accommodated after the decimal point range from 0 to 9. So you can have 0, a combination of 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. These are the digits that can appear after the decimal point. Okay? So, again, remember, the first thing we have said is that rational number system is denoted by this kind of Q, a Q with double stroke. So when you write your Q and you put a double stroke, this represents a rational number, or the rational number system. Number 2, rational number system is defined as a set of all x such that x can be expressed as a ratio of two integers, a and b, that is, a and b must be integers, such that b, the denominator, must not be equal to 0. Now, again, another thing you must note is that for this reason, results that could not be accommodated in the natural number system, such as 6 over 7, 7 over 6, 2 over 3, fractions were not accommodated in the natural number system. Fractions were not accommodated in the integer number system, but there should be a system that accommodates results that are a ratio of two integers, and that is where the rational number system comes in. So, whereas 6 over 7 were not accommodated in the natural number system and integer number system respectively, 6 over 7 can be accommodated in the rational number system. So, in the rational number system, fractions, ratios of two integers are accommodated, and that brings about the statement that clearly the natural number system is a subset of the integer number system, and the integer number system is in turn a subset of the rational number system. Now, take note of one thing again. How can you look at a decimal? The first statement is that every rational number can be expressed as a decimal. So you take note of that. Every rational number can be expressed as a decimal. Now, when you represent a rational number as a decimal, you can actually tell whether or not the decimal is truly from a rational number. So any decimal you see may come from a rational number or may not come from a rational number. So how can you look at a decimal and tell that this decimal must have come from a rational number? You can start with doing this. Every rational number can be expressed as a decimal, and expressing a rational number as a decimal means that writing it as a dot a naught, a subscript 0 dot, or point a1, a2, a3, and so on. Now take note, every number after the decimal are called digits. Okay, the numbers after the decimals are called digits, and the digits that can occur after the decimal range from 0 to 9, meaning that from 0 to 9 you can have any combination of digits after the decimal here, and the numbers after the decimal are called digits. Now, how can you look at a decimal and tell whether or not it came from a rational number? If a decimal has a finite set of digits, it means that that decimal was surely from a rational number. 1. Number 2, if a decimal has recurring number of digits, then that decimal must have come from a rational number. So those are two ways to know that a decimal must have come from a rational number. So what does it mean? Let me show you now. Now, for example, if I give you 0.83, for instance, and ask you, is 0.83, did 0.83 come from a rational number or not? The answer is yes. 0.83 actually came from a rational number. Why? Because A3 is a fixed block of digits after the decimal point. So this kind of decimal is called a finite decimal. Why is it called a finite decimal? It is because it has a fixed block of digits after the decimal point. So in this case, your A0 is 0, this is your decimal point, and your A1 is 8, your A2 is 3. Okay? If I give you 0.75, 0.75 is a finite decimal. And once you see this, a fixed block of digits after the decimal point, it means that this decimal must have come from, this decimal must have come from a rational number. Okay? Now, look at it. You can write your 0, or let me even call this 1. So this is 1.75. If you call it 1.75, it is still a rational number that must have given rise to this decimal. And you can write it as A0 equals 1, A1 is 7, and A2 is 5. You can have 1.855 to be a rational number, a decimal coming from a rational number. And let me call this, in particular, let me call this 14.855. Now take note, these digits are the 3 digits after the decimal point are 8, 5, and 5. So this number here, this 14 here, becomes your A0, while 8 is your A1, 5 is your A2, and the second 5 is your A3. So this is also a finite decimal. Okay? Now, so whenever you have a case of finite decimal, what it should tell you, or what you should know, is that this decimal must have come from a rational number. So only rational numbers produce finite decimals. Again, another type of decimal that rational numbers produce is what we call recurring decimals. So you may have a number like this: 0.83525252, and it keeps on like that. You will notice that 525252 keeps repeating. Now, when you see a decimal like this, take note, this kind of decimal is called recurring decimal. Why is it called recurring decimal? It is called recurring decimal because after a fixed set of digits, the fixed set of digits in this case is 8 and 3. After a fixed set of digits after the decimal point, notice that every other digit reoccurs. That is, they keep repeating themselves: 52, 52, 52, 52. It keeps on like that. So this decimal is a recurring decimal, and only rational numbers produce recurring decimals. So how do you know that just looking at a decimal, that decimal must have come from a rational number? It is if the decimal is finite, is a finite decimal, or it is a recurring decimal. Another example of a recurring decimal may be 17.235545545, and so on. Now, notice that the fixed block here is 2, 3, and you keep having the repeating block 545, 545, 545. So this is also a recurring decimal. And like I said earlier on, recurring decimals only come from one type of number. They come from rational numbers. Okay? So, now, what I want to tell you is this. Looking at these recurring decimals and these finite decimals, I want you to know that aside the fact that these decimals can only be produced by rational numbers, the next thing I want you to see is that you can actually convert a finite decimal back to being a fraction, a rational number. And you can actually convert a recurring decimal back to being a fraction. So the question is, how do we do that? Now let us assume that x is a rational number. Assume that x is a rational number producing a finite decimal. So let's assume that x is a rational number that produces a finite decimal. What I'm trying to show you here is that once you have a rational number that produces a decimal, you can actually move backwards from that decimal back to the number that produced it. So if x is a rational number that produces a decimal like this, a finite decimal, that is a0 dot a1 a2 a3 up to ak, then we can actually convert this decimal back to this number. How can we do that? We can do that by writing this as a0 the first digit or the digit after the decimal point, plus A1, the first digit here, all over 10 raised to power 1, plus A2, the second digit, all over 10 raised to power 2, plus A3, the third digit, all over 10 raised to power 3, plus you can continue up to AK, all over 10 raised to power K. Okay, now if you do this and simplify it, it will give you the rational number that produced the decimal. Okay, now let me show you an example. Let's assume that you were given this. Let's assume that you were given your x to be 0.83 like I gave earlier on. Now you can actually find what x is by moving backwards. Now this is the same as writing 0, the number before the decimal, plus 8 over 10 raised to power 1 plus 3 over 10 raised to power 2. Okay, now if you look at it critically, this will give you 8 over 10 because 10 raised to power 1 is 1, and 8 over 10 plus 0 is 8 over 10 plus 3 over 100. Okay, now that is what you have. Let's see. So if you continue, excuse me, so if you continue to get a final result, let's see what it gives. Let's see what that gives. So you can actually continue this to get this down. Let's see. So if you continue to simplify, you end up having that x, when converted back from decimal to fraction, will give you the LCM is clearly 100. The LCM of 10 and 100 is 100. So this will give you 10 into 100 is 10. 10 times 8 is 80. Plus 100 into 100 is 3. 3 times 100 into 100 is 1. 1 times 3 is 3. So you end up having the fraction to be 83 over 100. So this is the number that gave rise to this, 0.83. Okay, so what am I showing you? I am showing you that if you assume that a rational number x is producing a finite decimal, then you can actually go backwards move from decimal back to the number that produced the decimal. Okay, and for you to do that requires you to do this. Now let's see, what if I wanted you to convert 1.75 back to the fraction that gave rise to 1.75. So x is your 1.75, and you can write it as 1 plus 7 all over 10 raised to power 1 plus 5 all over 10 raised to power 2. And that will give you, take note, 1 is the same thing as 1 over 1. So that will be 1 over 1 plus 7 all over 10 plus 5 all over 100. Now what is the LCM of 1, 10, and 100? The LCM of 1, 10, and 100 is 100. So 1 into 100 is 1, is 100. 100 times 1 is 100. Okay? Plus 10 into 100 is 10. 10 times 7 will give you 70. Then 100 into 100 is 1. 1 times 5 will give you 5. So this gives you 175 all over 100. So this is how you get the digit, or the number rather, the rational number that produced that particular decimal. Now, so what if we assume that x is a rational number, producing a recurring decimal. So if x, the rational number, did not produce a finite decimal but produced a recurring decimal, how then do we convert? For us to convert, we can do that simply by actually writing this. X equals, you can write this as x equals A0, A1, A2, A3 up to AK, remember, and B1, B2, B3 up to BN. It keeps repeating B1, B2, B3 up to BN, and it keeps on repeating in these blocks of B's. Okay, now you can also convert this. How do you convert this back to the fraction that gave rise to this decimal? You can do that by writing A0 plus A1, A2, A3 up to AK all over 10 raised to power K plus B1, B2, B3 up to BN all over 10 raised to power k plus n minus 10 raised to power n. Now, if you use this, you will end up getting the number that produced that decimal. So what is actually happening here? You will notice that the first thing you do is to separate it, the decimal. If you want to convert this decimal, this recurring decimal, back to the rational number that gave rise to it, then take the decimal before the point, put it here, plus the fixed block of digits. Notice that A1 to AK is a fixed block of digits. So you now write that fixed block of digits all over 10 raised to power k, the number of digits you have in that fixed block. So there are k digits in that fixed block. Plus, you will now write B1, B2, B3 up to Bn, the recurring block, all over 10 raised to power k, the number of digits in the fixed block, plus n, the number of digits in the recurring block, minus 10 raised to power n, the number of digits in the recurring block. Now let us see. So if I gave you this that we did earlier on, if I gave you this to convert 0.83525252, if I wanted you to convert this back to the fraction that gave rise to it, take note, look at it again. So this will be my x, this will be my x, and if it is my x, it means I can write x as 0 plus the fixed block of digits 83 all over 10 raised to power 2, because there are 2 digits in that fixed block, plus 52, the one block of the recurring digits, all over 10 raised to power 2 plus 2, 2 here standing for the number of digits in the fixed block, and this other 2 standing for the number of digits in the recurring block, all minus 10 raised to power 2, the number of digits in the recurring block. So this will give you 83 all over 10, 10 times 10, which is 100, plus 52 all over 10 raised to power 4 is what you have here, minus 100. So this will be 83 all over 100 minus 52 all over 10,000. Okay? Because 10,000 is 10 raised to power 4 minus 100. So this will give you 83 all over 100 minus 52 all over, remove 100 from 10,000, that will give you 9,900. Okay? Now, if you take the LCM of 9,900 and 100, it will give you 9,900. Now, 100 into 9,900 will give you 99. So this will be 83 times 99 in one bracket, minus 9,900 into 9,900 will give you 1. 1 times 52 is 52. So that will now simplify to 83 times 99. Now what is 83 times 99? 9 times 3 is 27. So write down 7, carry 2. 9 times 8 is 72. Okay? 9 times 8 is 72. So 72 plus 2 will give you 74. 9 times 3 again is 27. So you write 7 and carry 2. 9 times 8 is 72. 72 plus 2 will give you 74. So that will give you 7. 7 plus 4 is 11. Now you now bring a 1 here. 1 plus 7 is 8. 8 plus 4 is 12. Carry 1. This will give you 8217. So the fraction is now 8217 minus 52 all over 9,900. Okay? And that will now give you, if you subtract 8 from 8217, if you subtract 52, you end up having 7 minus 2 giving you 5, and 21 minus 5, in this case, giving you 16. So this will give you 6, and this will give you 1, and this will be 8. So the fraction that gave rise to that problem, this decimal that we just talked about, the fraction that gave rise to that decimal, that is this decimal, was actually 8165 all over 9,900. Okay? Now, the last thing I want to show you about rational numbers, the rational number system, is this. Take note, for recurring decimals, you can actually write, instead of writing 0.83525252 ... provided you have recurring digits there, all you have to do is just to write it as 0.8352 bar. Okay? This 52 bar stands for the fact that 52 is the recurring component in this decimal. So if I gave you a thing like x equals 5.3612945 2945. If I gave you something like this, you can actually use a representation, another representation, to represent a recurring decimal, and this will be 5.361. And then from where you now start having the recurring digits, all you have to do is just to put the recurring digits 2945 and put a bar notation on top. That tells anybody who sees this that that is the recurring component. Okay, so if you have x equals a0 dot a1 a2 a3 up to ak, and you have b1 b2 b3 up to bn times okay, not times, but b1 b2 b3 up to bn again, repeating itself, dot dot dot, then you can simply write this in abbreviated form as a0 a1 a2 a3 up to ak, the fixed block of digits, and you can now write this b1 b2 b3 up to bn, the recurring block. So you only have to put this bar all over it, and it will give you a representation that is simpler to follow. That being said, thank you very much for watching this video. Thank you very much for your shares and your likes to our videos. Thank you so much. Thank you so much, and thank you so much.